Hi everyone, Mrs. Besega here, and today we're doing the third right-hand rule. This is the right-hand rule that determines the direction of magnetic force given a current and a magnetic field. We know magnetic fields act on moving charges, i.e. currents, to create magnetic force, and we know that their directions are all mutually perpendicular to each other. The rule is, I need current to be perpendicular to field in order to get a force. All of them are mutually perpendicular to each other. So let's get started. In order for these to be mutually perpendicular, if the current is to the right, that means the force can't be either right or left. The x direction has already been used up. The field, well, that's these x's here. And the x symbol means out of page. That's in the z direction. So the x and z directions are used up. That means the force can only be either up, the y direction, or down, the negative y direction. And from here, we apply our right-hand rule. So I want you to make a high five slap. Notice that when you take your right hand, you have a right angle that occurs between your thumb, your fingers, and your palm. The direction your palm moves is upward. So that upward direction, imagine a vector leaving the center of your palm, is perpendicular to your thumb and is perpendicular to your fingers. The right-hand rule is used because it shows all three of these as mutually perpendicular. Now that I've got it narrowed down to left and right, point your thumb in the direction of current. I know my thumb is going to point in the direction of current because I only have one thumb and there only is one current. Then your fingers are going to point in the direction of field. F for fingers, F for field, plus notice there's like a lot of field lines. In this case there's 12, and I have way more fingers than I do thumbs. When I do this, I'm going to point my thumb to the right. My fingers have to point out of the page, and that's kind of funny to do on this screen. This puts my hand facing down. Imagine holding this wire in my hand. The force would be down towards the bottom of the page. Whatever direction my palm faces is the direction of force. Once I got it down between up and down, once I narrowed the field down to just the y direction, the force has to be in the negative y, downward direction, in order to be mutually perpendicular. Let's try another one. So we have to make sure it is mutually perpendicular. I'm going to take my current perpendicular to field, perpendicular to force. Current is in the y direction, or technically the negative y direction. It's down, so force can't be up or down. Field is in the positive z direction because it's out of page. That means my force must be in the x direction, which gives me only two choices. The force could either be right or left. Now let's apply the right-hand rule. Point your thumb in the direction of current, so that's down, fingers out of the page, and my palm can push this wire to the left. So the force must be left. Notice that's the negative x direction, left. Well, what happens if something isn't mutually perpendicular? If you had a problem like this, well, that doesn't work. Notice the current is not perpendicular to field. One way you could think of it is you could think of it as these particles, the electrons that are flowing as part of the current, aren't interacting with any magnetic field lines. They pass right through them. And since it's not perpendicular, this force is 0. So not only is there no direction to force, the force magnitude is 0, that particle would keep moving in a straight line, going at constant velocity, object in motion stays in motion. You remember that, right? The force is 0, no need to do any math or right-hand rule. If these are parallel instead of perpendicular, the force is 0. One more practice, actually 2 more practice. So we're gonna narrow it down. Current must be perpendicular to field and perpendicular to force. Current is in the z direction. It's negative z into page. That one's already taken up, so nothing else can be in the z direction. Field is going up. Notice there's several field lines. There's several fingers on your right hand, 4 of them for most people. This is in the positive y direction, up. So nothing can be in the z, nothing can be in the y. That means force could be either right or left. And now that I've narrowed it down, right hand rule this. Put your single thumb in the direction of current into the page, just like literally put it on the page. Point your fingers upward towards the top of your page. See how my palm pushes to the right? Whatever direction your palm faces is the direction of the force. So it goes to the right, that's the positive x direction. Now, my last 2 examples are trickier, and you'll see why. One example is trickier because I've given you the current, and I know current is perpendicular to field, is perpendicular to force, but I haven't given you the field direction. In order to get the field direction, notice that fields point away from north and towards south. So if you're stuck on 1A in the homework, do this first. Field points from north to south. The field points to the right, that's the positive x direction. The current points out of the page, that's what the dot symbol means. Notice that means the current points up towards you. That's perpendicular to the field, which points right. And if both the out of the page, positive z, if both the out of page and right directions are taken, that must mean the force can be in the y direction. Must be either up or down. Point your single thumb in the direction of current. Point your several fingers in the direction of field to the right. And notice that means my palm can push this wire upward. Force must be in the positive y direction, up. Last example. What if you know the direction of force and you know the direction of field? Can you find the direction of conventional current? Why, yes, you can. They still must be mutually perpendicular to each other. So I'm gonna still write this out. Force is perpendicular to field, is perpendicular to current. My force is in the positive x direction, so that's to the right. So the current can't be in either the left or right direction. The field is going out of the page, that's positive z. And do notice that the current could only possibly be up or down anyways because the current has to travel through this rail. So I'm choosing between up or down. I kind of knew that because that's where the wire is. The current has to run in the wire. Okay, so I'm choosing between up and down. Now, right hand rule this. I need to put my palm to the right and put my fingers out of the page towards you guys. So my fingers are out of the page. My palm is pushing this rail to the right. And that means my thumb points upward, positive y direction. So current must be going up. If I want to complete this circuit, if conventional current is going up, all right, then it's going to do this, complete the circuit. It's conventional current, so it's going away from positive towards negative. and my circuit is done. Now, if you don't want to see another method on how to do the right-hand rule, you're done. If you would like to see how to do what's called the cross product, then feel free to continue watching this video. Now, in our universe, we know that the current and field create a magnetic force. And when I put that X there, that's actually not a straight up regular multiplication like you're used to. That's something special called the cross product. The cross product takes this vector of current and the vector of field to get the vector of force. Technically, in order to get the magnitude of force, I'm actually going to write this is ILB sine theta, where theta is the angle between this IL vector and B. Now, for our purposes in 5470, these are always going to be perpendicular to each other. So sine of 90 degrees is 1. So we can call it ILB and drop the sign. But there's another thing with cross product, besides the fact that it should have a sign component factor to it. And that's that cross product is directional and anti-symmetrical. Ooh, words. All right, so let's show you some examples. Let's say I do the cross product of x and y. X cross y. X cross y gives the z direction. In order to have three things mutually perpendicular, the cross product requires that x, y, and z are related like this. Okay, so now let's do some permutations. I'm going to say y cross z equals x. By shifting everything down 1, so I've shifted y to the first position, z to the second position, and x through, I now have up cross out of the page equals right. All right, let's make one more permutation. So this means z cross x equals y. This permutation, where I'm taking y and z and moving everything down one row, this gives me directions. So you know what? I have one that works like this already. Do you notice in this example, we have y cross z equals x? We actually have that right here. Y cross z equals x. This statement where it's up cross out of the page equals right, that actually can get us the right-hand rule. So let's see if we can match these up. So using the right-hand rule, y cross z equals x. The x direction is to the right, so my force has to be to the right. Let's try another one. Z cross x equals y. Z cross x equals y. Oh, we're so good. All right, let's try this one. With this one, hey, the reason this didn't work is because when I do IL cross B equals IL sine 180 degrees, the sine of 180 degrees is 0. Cross product explains all of these, but the problem is you've got the directions for cross product. However, we haven't dealt with this anti-symmetrical thing. What if I had a negative sign? Right? Let's say I take this last example and I add a negative sign to x. Z cross negative x. I should get negative y. Right? Negative signs are going to carry through just like normal, but what if I do something funny? What if I switch, instead of permutating, instead of rotating these through, what if I switch x and y? Y cross x. You actually don't get z. That messes with people because they're like, wait, but if 2 times 3 equals 6, shouldn't 3 times 2 equal 6? Nope. In cross product, anti-symmetry means that if you take any of the 3 original permutations where everything is positive and you flip the order x cross y into y cross x, you get an anti-symmetrical. It gives you negative z. Let's see if I can find one of those. What if instead of z cross x equals y, what if instead I had x cross z? If I switch the order of these two, x cross z would give me negative y. That predicts my force in this case. Because it's not z cross x, it has a negative, and negative y is down. Now, my last 2 examples use this negative signs. Cross product has 3 factors. It has the sign factor, which explains why parallel vectors don't create a force. It has this anti-symmetrical thing where you have your 3 original permutations of x cross y equals z. In the 3 anti-symmetrical permutations of z cross y equals negative x, taking these and just switching the 2 products, right? And finally, the negative signs. Take any one of the 6 products and throw a negative sign. Let's say I put a negative y cross z. I would be taking y cross z. Example, carrying the negative sign through, I'd get a negative x. Negative y cross z is negative x. This can be used to predict problems. So what if I had negative z cross y? Z cross y was here. I have negative z cross y, so I'm going to take my product from up here. That gave me negative x before. Now with the extra negative sign, I expect positive x. Now, as I said, cross product, totally optional. It is nice to have a way to check your work though. So let's do a problem where I don't draw out anything at all. Let's say I have a current of 50 amps to the right and a field of 4 Tesla into the page. And I want to find the force. And just for funsies, I'm just going to make L equals 1, so that's nice and easy to deal with. 1 meter of wire. That means the magnetic force is IL cross B, or ILB sine 90 degrees, because right and into the page are 90 degrees off from each other. This gives me a force of magnitude 50 times 1 times 4, so that's 200 newtons. And to get the direction, it's I, so that's right, X, cross B, that's into the page, that's negative Z. I go to my chart. X cross Z is negative Y. But with the extra negative sign, that makes it positive. Positive Y is up. If you want to check with drawing this out, you can totally do that. So this is current to the right. B is into the page. That means the force must be either up or down because the X direction and Z direction are already taken. And if you right hand rule that, thumb points to the right, fingers into the page, palm is up, that force is indeed up. Great. So hopefully you got at least the right hand rule, and if you want to learn how to do cross product, hopefully that helped. Otherwise, best of luck.